So thanks Nihal. Thanks for giving me this wonderful session opportunity here at the Microsoft. And the outset, also very good morning to everyone, and welcome all of you. And just before this started, I just went around to understand the background of people here. There are a few new additions, but in general, I kind of understand it's a mixed audience. So we'll do it very differently. And I don't know if you have attended some of my talks before, but I give a lot of impetus on intuition. So there will be a lot of math in this, but that math will be kind of little bit sanitized and given so that it's not equations for the sake of equations. So the general idea is to understand fine tuning from a lot of different angles. To understand fine tuning, first of all, we'll have to understand what are we fine tuning? What is the ecosystem that we are in? So at the end of this talk, I've got two objectives. One is for you people to kind of have a little bit of geometric visualization, even though it may not be perfect, about like in a vector space, how are you going to think about things that are happening? That kind of intuition I would like to develop. The second thing is I want also you guys to understand a little bit of the expressivity of this large language model ecosystem, how expressive this is, and what are the different parts of this ecosystem and why they are planned that way. And when we are doing fine tuning, why are we doing it in a certain way? And there are different ways in which we'll try to explain fine tuning today. So those are the two objectives that I want you guys to take home. Now, the thing that you see on the screen is going to be our agenda. So I've cut that into three parts. Um, to make it a little easier, I will break at each part so that we can take some questions before we go to the next part. I think that there's a logical break in all those places. Now, the first part is going to be, I'm going to be little bit overwhelming you with the landscape of fine tuning, because not a lot of us will understand that fine tuning has a larger landscape than the simple keywords that we have been hearing. Okay, so we'll get a little overwhelmed first and then slowly get into LLMs and come back to the same landscape, and now we will familiarize ourselves. Okay, so that's the process we'll go through now. The first part is going to be a little bit of the landscaping, the fine tuning landscape, the philosophy of LLMs. I know there are a lot of students in the audience. There could be some new information seekers also in the audience who are non-students, and there could be a similar category in the online crowd itself. So for them, we'll have a philosophy of large language models and what is at the heart of LLMs. That's very important. So we'll understand that a little clearly, and slowly we'll move into how do we then leverage them. And one of the ways to leverage LLMs for our purpose is fine tuning, and we'll walk through step by step what really happens during fine tuning, and then we'll go into all this all these buzzwords, PEFT, LoRa and all that, and look at how it's working, and a little bit of a code snapshots just to make sure we understand the flow. That's going to be, the party is more going to be like the few things to come, etc, etc. Awesome. So very quick introduction to the landscape. Just one quick show of hands from the audience, at least in the group here. How many of you have seen this kind of a figure before when it comes to fine tuning? Awesome. So this is kind of very new to you, right? Okay, awesome. So this is one of the recent papers, and the credit is given here. Layalin et al. This is very recent paper. It's a very good summary. I would encourage all of you to first go and revisit this paper here. So we should not be lost in the keyword, so that, and we should logically organize the thought behind different ways of fine tuning. So this one picture in that paper was very nice. So I thought this is a good starting point for us, and we'll keep revisiting this figure again and again during the talk. Okay. So this figure basically has five key things. One is the whole landscape of additive fine tuning models. So when I say additive, what really means is based on whatever you have as a pre-trained model weights, you add some more model weights along with that. So that's the whole family of additive fine tuners. Now in that there are few subfamilies. There are soft prompts and there are adapters. And we'll have a slide for each of them. We'll come back and understand what they are. But for now you understand that these are the different ways of adding your own weights into it. Still under the family of additive fine tuners. And you exactly know where to add what, and that's why it's in that nice cozy circle there. But if you are very selective and you're not programmatic, you're very selective, you're randomly picking up a layer from inside and fine tuning. And we'll talk about what is a layer and what are we fine tuning. That's going to be the next slide. But for now, put a placeholder and say that we are fine tuning something, and there are a bunch of things we can fine tune, but we are randomly selecting something. That is the selective class of models. And the last one here is the reparameterization, where our famous LoRa, most of you would have heard about low rank approximation. So we will talk a lot about LoRa in this. So this is the mental image first we would like to have before we go into each of these. LoRa is the one we'll go in a little bit more depth than the others. The others will still be introduced, but we'll see. Okay, one of the great slides, and that's Lex Friedman. If you have not known, he runs a good YouTube channel. You can go visit that. So one of the nice ways of explaining a transformer. Now, why are we starting with transformers in this? Now, transformers are basically the action blocks of our LLMs. Think about transformers as something like a transistor for your hardware PC. And put a bunch of them, wire them together, and that's kind of your LLM. If you have no background in LLM, think about it like this. And even within transformer, there are a lot of different. Transformer is a very complicated machinery, so there are a lot of moving parts there. So we'll go through a lot of these moving parts, and this is the action block, but the exact workhorse inside that action block is going to be something called self-attention and the attention weight mechanism. So its role in fine tuning is very important. So that's what the two slides from now we are going to talk about. But this is a beautiful explanation of the beauty of transformers. I would like to spend a minute or two in explaining that. One is it's very expressive in the forward pass. So when we do something on the forward pass in a neural network, what do we typically do? We typically like to model it in a very rich way. The representation learning has to be richer and richer, so that for the downstream tasks we are able to do our sequence classification or a summarization or etc., right? So the representation learning part, for that to be very good, the modeling artifacts that we place inside should be very expressive. Now this transformer, which is kind of a general purpose differentiable software-ish computer, right? So it's got a very nice expressive architecture inside, and next slide is going to go through that. The second thing it does is it is very optimizable also. Though we are going to model any kind of sharp functions, we want the necessary smoothness and differentiability that flows back in our backprop step. So this is another beauty of the way in which transformer is constructed. And the last one is it needs to be efficient. We need to put a lot of parallelization machinery into this framework so that we can create a lot of kernels that can immediately parallelize and push it across GPUs. In our case, for people who already know this, the self-attention itself can be kind of parallelized because it's kind of one vector dot product is independent of the other when we do self-attention, and when we add multiple heads to it, the multiple heads are also parallelizable. So it is a beautiful parallelizable ecosystem. We're in a safe universe. So with this kind of a background, let's go a little bit deep. Let's understand this action block, okay? Again, don't get overwhelmed. This slide is a beautiful slide picked up from Dr. Sergey Levin, UC Berkeley. Now, in one slide, the whole beauty is actually exposed here. So so initially all our weights, all our input tokens are passed here, and you would have known something like positional encoding. The input token could be something like, for example, uh, the bank of a river, bank of the river. That could be a token, right? So that's some kind of a token which enters here. Now each layer inside this transformer is a very beautiful activity. Now when the token by itself goes, the relative position and the importance of or the significance of each of the alphabets in that position is not really captured, for which we are using the input embeddings with a positional encoding. So we actually combine these two, concatenate this, and then send it to our first multi-head self-attention. Now, what is multi-head attention? We're going to talk a little bit in detail because that's where we're going to do a lot of fine-tuning on. So it's very important that we get a little bit of basics. So once we go a little bit into this, we take our input, we take our input, we take input embedding, which is converting our words into vectors, and take the positional encoded vectors. Now this has got contextually aware information, and then it gets into our multi-head self-attention. Now the multi-head self-attention in itself is not a very highly non-linear beast. If you really think about it, it's just a linear layer. Again, q k transpose scaled by 1 by root n, all that, right? So that's just a very simple dot product, and then that is again dot v. The only non-linear part comes in the softmax of that. So that non-linear part is also something just to add your weights on. Now, the reason why there is a feed-forward network here is to actually push in that non-linearity. And why you need non-linearity? You need a lot of expressiveness. You need your model to actually pick up all these non-linear edges and artifacts, right? You need a lot of modeling paraphernalia which are non-linear in nature. So these weights that the W2s that you see here, the W1s that you see here, and the ReLU that you see here. The W2s and W1s are the trainable for the trainable parameters, and the ReLU, all the ReLU at each of those neurons, that adds to your nonlinearity. It could be any activation function, and there are few bias terms, and there you get your nonlinear. So every transformer block, and there will be multiple such blocks in our LLM. Okay, and when we are exactly fine tuning, we are operating a lot in this space. We're operating a lot in this space, but the overall architecture gets its nonlinearity because of all these feed-forward networks. And if you think about these layers, which are add and normalize, like there are these skip connections. So you add the whole input, the context-aware input with the attended input, right? So these two are added and they are normalized. We are talking about layer normalization here because we are sending every token after token. So there's no batch concept here. So this whole thing is added and normalized, which means that we have a lot of smoothness flowing back and forth when we do this back propagation. So think you have multiple such pieces which are just tagged one over the other. So there is a big, so what does this part here do? Bank of the river. Now I'm not talking about a bank that is dealing with currency. I'm not talking about a bank like a verb. I am banking on you for this job. Because I've got bank of the river, I'm talking about a river bank. So it contextualizes my information, right? That's very important to understand intuitively what transformer does. So what self-attention, multi-headed self-attention is. So a multiple such blocks which are chained along, which will give you some initial context, chained with the next context, chained with the next context. You can actually draw a parallel with a lot of small dots and edges, giving it to shapes of objects, giving it to parts of objects. This is the object itself, right? That's how you go through the CNN, your typical convolutional neural network. So think about transformers building the same for you, giving a lot of context. It draws from some context, and from that context it draws higher level context, and it keeps drawing these contexts. Think about transformers, a bunch of transformers stacked together, which is an LLM doing that. So now think what LLM is really doing. What LLM is really doing inside is actually building or learning the statistical patterns of whatever you used it to train for. That's exactly what LLM is doing. It's finding all the statistical patterns in the all among all the corpus, and depending on the way in which you train these LLMs, the knowledge representation and the knowledge emphasis is going to be on different statistical patterns. So that's exactly what LLM is doing. Now, because this is a very complicated thing, it is very hard, even if I exactly tell you this is a 22 layered LLM with 22 transformer blocks stacked against each other, to exactly explain why in such high dimensions, why such a thing happened. To exactly explain is going to be very difficult. There are some explainable things like the transformer rollouts are there. You can have some visualization, but understanding why it behaves such way in such a way demands the knowledge of the corpus that first of all went in, and the supervised or unsupervised or reinforcement learning ways that you use for training that corpus, how you generated those weights. So all this knowledge you need to have apart from the architecture and the weights knowledge to exactly tell what is going on inside. So we are in such an ecosystem, we are trying to now fine tune. Now, first let's get 2-3 terms out of our way. There's something called prompting that we always do. It's kind of an implicit fine tuning. It is a way of fine tuning. It is an implicit fine tuning. Actually it's called in context learning. So when you few shot, people have done few shot prompting. By the way, prompting, I have a slide which I'll show a prompt. So in that I will explain a little bit more clearly. Now prompting is slightly different from fine tuning, which is fine tuning all the layers, which is different from transfer learning, which is also different from yeah, these three are different, which is also different from the fourth one, which is RAG, retrieval augmented generation. If you think that's a lot of jargon, just wait for some more time. We'll demystify all these things. So this is our transformer sense. This is the sense we need to understand, this transformers, and this is exactly what we need to focus on now. This is where the whole attention part comes. Now the attention part comes as a trained, learnt matrix, attention weights. In our case, for simplicity, we can take it as a two-dimensional matrix, some n by n matrix, like bank of the river, right? Bank with bank, bank with of, bank with the. So bank with of, bank with bank, bank with the, bank with river. So there could be some, all these can be converted into vectors. There's a process which we can rewrite the vectors and we can get these y's. So when one thing aligns to the same, we get a wxx kind of weight, and then you get wx, y plus 1, y plus 2, whatever it is, x plus 1, x plus 2. So you get all these things, and these are the weights that you are actually loading on your given context to give your output. So you are finally making these things learnable. That's what you're actually doing when you set up this problem. Now, so again, the order, the non-linearity, the shape, and all that is there, but that's not the purpose of this talk. But once you get something like this, what happens is you can actually pass something called a query, key, and value, the three similar dimensional matrices, and you can train all the weights of these matrices, and you can keep all the statistical pattern that you see in this corpus as weights of those matrices. With those weights, then you add non-linearity and the non-linear weights, the softmax loadings, and all those things also can be trainable. So now you get a very huge trainable machinery. Okay, so now if you think about so this is very important, and just because we spoke about dot products, I can also explain a little bit about what happens here. The T is the number of tokens. So you would have said famous formula Q K transpose divided by root T softmax of that term dot V, right? So that's exactly your your self attention, and if you do it over multiple heads, which means that the bank of the river is long, if the sentence is like that, So what is the bank? What is the river? There could be one head that would think about disambiguation, and there could be another head which would think about the bank and the length. What is the length of the bank? There are different characteristics in your context that can be captured by different heads. That is why you have multiple heads. So the multi-headed, some kind of a self-attention matrix which is trainable like this. So that's our context in which we are going to apply the fine tuning now. We're going to fine tune this kind of a matrix here, and this is again a square matrix, and that's because you can have two query and key matrices of some dimension and two key transpose, and you can make it you can mat multiply, and the moment you mat multiply your query and key, you got t by d, and d by t you get t by t, which is your square matrix. And then optionally you can make this top diagonals as minus infinity, because when you do the softmax, e power minus infinity becomes 0. So which means this can be a masked self attention which are used in decoders. If you go back and see your, here you will see a masked self attention instead of just masked multi-added attention. So you're doing the masking because while decoding you want to know only bank of the, you don't want, if you want to do an autocomplete you should not know that it's a river, right? So for masked self attention you can use that, that's optional, that's why it's OPT. And then you do it softmax, which is basically e power qk transpose divided by root n dot p, and so that repeated over several heads. So totally you multiply it v, right? So that's your attention matrix. Now this attention matrix, the problem you can see with this attention matrix is it is n by n, right? So there are n square possibilities. There are n square things that you need to attend to, and every time my context length, bank of the river means it's 4, bank of the river, 4 tokens. So it's 4 by 4, right? 16. So as your context length increases, it's going to be a huge problem for you, because if it's 1000, it's 1000 by 1000, right? That's a huge context. So that's just one attention matrix of one head. So there could be multiple such heads, multiple such attention matrices, and multiple such transformer blocks tied together. Now you can see the parameter space explosion, right? Now the beautiful thing, and this is a good part to actually give the first selling point of this talk, and that's why I revisit this figure again. An LLM, think about LLM as a very complicated statistical data miner with very low intrinsic dimensions. So if you think about, we are living in a 3-dimensional world. Here, even if within this hall, the mass distribution in this hall is fairly even, because there are people everywhere, right? If I randomly draw, if I'm blinded, if I randomly throw an object somewhere, there's a high probability that it hits a human, right? But when and of course there is sparsity here also. As your number of dimensions keeps on increasing, this sparsity also increases proportionally, or kind of disproportionately, to be very honest. So there are a lot of sparse spaces, and there are very concentrated manifolds in which the mass is actually located. So this is kind of the fundamental property people envisioned, and also kind of verified with LLMs. So you are basically learning something which is very intrinsic, and you are over parameterizing. So in order to learn the statistical thing of a language, I'm actually over parameterizing on billions of parameter models. So I've kind of over parameterized. Now how do I reverse the story? Now that's good for training and getting a great result, but then I cannot now fine tune, because I don't have so much resources to dabble with so much weights forever again and again. That's a problem I'm hitting. Now just to be just a fun fact is, I think around 2018, the end of 2018, the VRAM of a GPU was roughly 12 GB, you can say. That's kind of the normal going around VRAM, available VRAM of a GPU. And right now we have like 80 GB. That's kind of become little normal with the 6,800. Now, if you look at the LLM, this is the explosion like 5x, right? 5, 6, 7x, whatever. If you think about the LLM, the parameter space, the BERT large model, I guess it was around 300 to 400 million parameters. That was the parameter space at that time. It was one of the highest. This was 2018, and not even half a decade. We are what? We have gone to GPT is what 175 billion and little more, and there are models with 1 trillion, right? I mean, so where is this? This is like 500, 600 times X. I mean, that's not fair. Like there's a huge explosion in one space, and the democratization is also not there. So the availability of things. So we need to come up with very smart ways of thinking about how do I fine tune this many parameters so that I get what I want from the kind of data that I have, which suits my purpose. But I also want to use all the general purpose learnings that these models have already got from reams and reams of data in which they were fine tuned. I mean, isn't that beautiful if we get such a good mix of both the worlds? So that's where we again come back to this. That's where we have LoRa, and there is this alpha parameter in LoRa which will exactly through which we can exactly weigh how much of general purpose information we want versus how much of the learnt information that we want, and we can always do that. Okay, so that's something that we can do, and we can also use something called soft prompts. I think I'll come back to that. There's a slide on that. This is a good time to sorry. Okay. Stay here only, not go there. Okay. If you want to point at something, you can also use this. Oh, awesome. This is the tab. Okay. Okay, I'm going to use this now because there's a lot of jump in my voice for the online attendees. So I'm just going to stay here. So what are the challenges of these LLMs? Now we got a mental picture, right? A geometry. The first take home that I said was we need to understand a little bit of what are the paraphernalia that we've got in hand, and geometrically get an intuition of what it is, what we are dealing with in high dimensional spaces. Now the second part that we're going to go is the foundation models, the challenges that they pose, and how are we going to tackle these challenges while fine tuning. The first one, the foundation models are tailored to respond to specific request types. Now it could have been generalized for different kinds of tasks, but it was already preset. So it does summarization, it does sequence classification, it does auto completion. So there are a bunch of tasks it was trained for, which it did perform very well, and we've got all these weights. Now I want to do something like a sentiment classification. Right? I just want to do something like that. Now it was not specifically trained for that, but it got all my statistical patterns. Oh, the movie that I saw yesterday was not up to the mark. The movie is a passe. These kind of sentences, it needs to construct all the statistical patterns out of this sentence to say that when I say the task is to find the sentiments out, it should immediately go and say, okay, I got based on all the patterns that I mined, and given the task that you are interested in, this is the most likely outcome. So it should say that, or I should make it say that without wading through all its 175 billion weights. So that's problem number 2 that we are attacking. The rest of the talk is going to be determined for that. The first one, we understood the context and the space. Now, given our understanding, now we are going to understand a little bit of intuitively how we are tackling this. Okay? Now, the foundation models are tailored to specific request types. They are constrained by the data that they have seen. There could be some years, like till 2021, I've got the data. I've not seen the data for this year. Till 2022, I've not seen the data for this year. Maybe the kind of application that I have is very useful if I have the current data, and it'll be great if I do an exponentially weighted moving average going backwards. So something like a stock market returns. I'm more interested in the current thing rather than some previous patterns, or the vice versa sometimes. Now, fine tuning is an option to also provide additional data to the foundation model. Now, the foundation model also has a great set of its own learnings. But see, look, I am a doctor. Okay, I've got my specialty in, let's say, immunoneurology, right? And or something like, or some aspect of neurology. And I know a bunch of ataxias that generally happen. So I can, instead of just going through all the terms in the Gale encyclopedia and teaching my LLM everything, I know what is a cerebral ataxia. I know what are the different types of it. All the 46 different types of disorders I can explain. How much of it is genetic, how much of it is autoimmune. I've got a document like that, right? I can put a symptomatology chart and add it to this. Now what I've made it is, I've already, it was trained on USMLE exams, so it already kind of a part doctor. It was also trained on PubMed. It was also trained on PubChem. But I have infused with my additional knowledge of cerebral ataxias, right? So this is beautiful. Then I make it a little bit of a specialist in itself. Now, how do I do it? This is called RAG, Retrieval Augmented Generation. So typically when you generate something out of AI without doing anything, that's just generative AI. But if you want to do some retrieval augmented generation, where are you retrieving it from is something that you define your own knowledge. That's called a RAG. And we'll talk a little bit about the RAG at the end. And that's one of the very useful things that we can use in our day-to-day application. Suppose I am a finance guy and I see a certain pattern in my invoices in my company, and I want to know the risk in tending to a certain compliance based on the vendor and the time and the kind of inventory and the kind of deliverable that has been promised. Then I know my thing better than what any LLM has ever trained. So I have my own RAG, my own database that I infuse into it, give it that knowledge along with its general purpose knowledge, and then I can make a risk reward model, right? So that's something. So here what we need to watch out for is the TCO, the data drift and the model drift. We'll talk about the TCO, the total cost of ownership. That's very important because if I go and set out to do the whole parametric retraining, right? Suppose I've got 1,000 documents with me. Now I need to, I can either do a RAG or I can just go and retrain my whole 175 billion parameter model. What is the problem that you guys see? There are two problems with that. What is the problem? Maybe I'll just throw it. Expensive. Right away it's expensive because I need to first of all set so much stuff. This is the second problem, which is even more.
It cannot be complete.
Okay, my 1,000 examples is not complete. It is resource intensive, which makes it expensive. True. Not enough data, which means what?
It's incomplete.
Yeah, it's incomplete. If you think about it, it's actually, you have a very high chance of overfitting. You're again over parameterizing, right? So many billion parameters, you have so much data, you're probably doing rote learning or not even rote learning. You're learning every point in it. Just so there are a lot of problems if you do that way. Okay. So the total cost of ownership is important. Whenever you're thinking about fine tuning, you should think what is the task that I am fine tuning for, how much data I have, what is the foundation model I am picking up, what was it trained on. There are a lot of criteria that you should think about. Okay, it's not very easy just to pick some off the shelf model and do something. The repercussions are going to be huge. The second thing is the data drift. So is it already with some data that has been already existing? You are trying to override that. So there's some beautiful publications. Just offline, you can contact me. I'll give probably some list where you can say that if you want to reverse the labeling, right? So if you want to give positive labels as negative labels, whatever it has learned as positive in the foundation model, if you just want to reverse it using your few shot prompting, the small models are actually robust to it. They don't give up. But the large models, they give up not immediately because they've got so many parameters to learn. They take your thing, they actually learn, and they kind of relearn later. Now this property is what, if you have heard about this, is called emergence. This emergence properties are seen. So when you are actually fine tuning something, you need to be wary of all these things, like the foundation model, which corpus it was trained on, what is my task that I'm training it for, and how much data sets that I have, and is there an is there an overfitting possibility, etc., etc. Okay, so these are some challenges in LLMs, and if you think about something like this, right? There is a GPT-3 Da Vinci thing, and there's a Text Da Vinci 003. There's a base model there, and there's a fine-tuned model here. So for people who are little newer to LLMs, a prompt is like you just give an instruction. It can simply autocomplete, or you can give a very detailed prompt step by step. So there you can see, tell me how to fine tune a model, and this is kind of a very zero shot way. You're just asking that question, it's giving you some stuff. Then you actually take that model, fine tune it. We have not really gone into fine tuning, but I'll tell you, if you fine tune it, and for that model, if you ask, tell me how to fine tune a model, it completes it in a certain way. Now, this is obviously much more palatable for humans, right? I mean, rather than simply giving some keywords and questions and sentences. This is much better because we had the task of zero shot prompting it and fine tuning it in a certain way. So it can so happen that the Instruct GPT 1.3 billion model, Instruct GPT 1.3 billion model can actually work much more efficiently than the GPT-3 itself, just because it has been fine-tuned properly. Okay, now we are slowly getting into fine-tuning. We are slowly getting into the modus operandi. Five simple steps. We have to choose the fine-tuning task. Now, in this simple example, I'm going to show the fine-tuning task for sentiment analysis. Okay, because that's something everyone will understand, irrespective of our backgrounds, right? There's a sentence, the review, and it's positive or negative. That's it. So choose the fine-tuning task. Prepare your training data set. Choose a base model, like all that we discussed. The base model could be anything. It could be a $175 billion model, or 7 billion, or 70 billion. You know what all those models are in the market, right? And then you can fine tune using some supervised learning. And finally, you can evaluate the model performance. This is the typical step, typical ML kind of step. One fine tuning part in the middle. That's three ways in which you can do, at a high level, three ways. You can retrain all the parameters. Of course, we just said it's expensive, all that, and it's costly, it's too exhaustive and all that. The second way in which you can do is just transfer learn. I want to know all that representation that you have learned, all the patterns that you have learned. I'm just taking your last dense layer out, and the layer that coils back to my output dimension. I'm just changing the weights of those two layers. Everything else I'm freezing, just unfreezing these two, training it for my corpus, just hoping it works. May work, no issues, may work. In most of the times, for general simple applications, it will work. If you're doing something very involved, RAG kind of thing, it will not work. Or if you have a lot of nuances in your fine-tuning task that you identified, will not work. A lot of scenarios in which it will not work. Okay? The third one is your parameter efficient fine-tuning. So the first one is not at all parameter efficient. Second one is parameter efficient, but you are not really dabbling with the expressivity of the LLM. You're not really doing a lot of changes. In the third one, what you're doing is you're having all your weights, and all your weights are frozen, and you're infusing. If you look at this part here, the gray ones here are some weights that you are infusing yourself. Now that might look a little counterintuitive. Wait a second, you just said that there are too many parameters, and all these parameters put together, if I start dabbling, first of all, it's over parameterizing. I might increase the bias. Second, it's not even possible because it's so expensive, right? But now I'm saying that I'm trying to infuse a little additional layers here. I'll come back to why I'm saying that. So then if I infuse a few additional layers, then I have a little bit of control, and this I'm just showing one hidden layer here. And of course, as you know, our network has like hundreds or thousands of these. Like everywhere, if I infuse some of these layers, and you can think about, I could almost be in the order of doubling this weights, right? Counterintuitive to start with, but it'll work. We'll come back to what is the trick there. So, and this trick is actually what is called the reparameterization. Why are we infusing something? Because we've got some existing parameters already set. However, we are re-infusing or adding something so that we can reparameterize it later. What I want to say is, we are not dabbling with the existing parameters, we are adding our new stuff, and we are dabbling with the new stuff that we are adding, so that it's kind of tuned in such a way that it modifies the general purpose knowledge for my corpus. That's what is going to happen. We'll go to the math of that a little bit. Okay, and here again, now you understand a little bit of additive sense, right? So when you add, you can add your soft prompt tuning, and you can also add your adapters here, and you can reparameterize it at the end. Now you can selectively randomly pick your layers and also do this. Now this figure has become little more familiar. So you exactly don't know what is all inside. Now it has become little more familiar. For what first time when I put this figure, it was Greek and Latin, right? So now we are slowly getting into it. This figure is becoming a little familiar. Now let's go one step forward. The key idea behind something called LoRa, the low rank approximation. And before we even get into this, let's understand. I'll take a 2 or 3 minute detour because it's very important. Nihal, how are we doing on time? It's okay if we take like 20-25 minutes, right? So, okay, awesome. Let's think about something that we all probably know a little bit: principal component analysis, PCA. Since we know, I can just ask a few questions. Uh, Apart from saying it's a linear dimensionality reduction, what does PCA do? Can someone tell me the heart of it? What does PCA exactly do?
Takes the vector space into its simplest components.
Beautiful, beautiful. It kind of it's kind of a change of basis. Your vector space is expressed into very good manageable components based on what? Based on what?
Highest varying components.
True. So the first component will be the one which is varying in the highest possible way. That's the maximal eigenvalue, and the second one is the second eigenvalue. But then, how does it do that? If you think a little bit about it, right? Suppose you've got a 7/3 kind of a matrix, right? What I mean, if you think about principal component analysis, covariance is very important. It's kind of related to our self-attention also, in a sense. The covariance is, if you take a 7/3 and just do thing like A transpose A, something like that, right? What you're doing is, you are, let's say 7/3, 3/7 is 7/7, right? Or 3/7 into 7/3 becomes 3/3. So when you want to get these three major principal component axes, you take the covariance of the matrix. So think about your data. This is a three-dimensional space. I spray some data points here and there. Let's say I spray a data point near that chair, and I keep on spraying it in a diagonal, and I hit that particular door there. From that door, it's like a line, these data points are sprayed there. Now, do I need all this three dimensions to represent that line? No, right? I can actually make the dimension, I can reduce the dimension. I can just, first of all, I can do it in two dimensions. In this plane itself, in that plane itself, I can capture that. The plane which goes as a triangle above and triangle below, that plane itself could capture that line, 2D. And even more, that line itself could capture. Line is just 1D. So I just need 1D information if the points in this are sprayed in this. Now go back to LLMs. What did we say in the beginning? LLMs are intrinsically, the intrinsic information of LLMs are in a very low dimensions. When we put all these transformer architectures together, n block and do it. We are in millions of dimensions, but the real intrinsic dimensions is very low. So we are trying to take advantage of that while setting up our fine tuning ecosystem, right? So in PCA we did that already. It's not something that is like the rocket science. So we did that in PCA. We took the covariance matrix. We took the eigenvectors of that covariance matrix. Of course, the covariance matrix has to be standardized or normalized in a certain way so that the artifact should not pull your eigenvalue maximization mechanism, because then you'll have to kind of subtract the mean, divide by standard deviation, whatever the way you want to standardize, and then in that you actually do the PCA, right? So when you do the PCA, now you get the basis which is aligned with that one line from 3-dimensional to 1-dimensional. Most of your information is captured in that 1 dimension, and since LLMs are intrinsically having their information stored in a very low dimension, they've always been over parameterized. We can use that trick to come back to this. Remember all those attention matrices which are huge in number? All these places we are going to do some kind of a trick. So here, think about it this way: the key idea of this low ranked approximation. The first idea that we see here is there is an input here, and there is an output hidden layer, and let's say this is the dimension d by k. So this is basically your WO, these weights here in the middle. So WO times your x, that will be your h of x. Okay. Now the dimension here is some d by k, some k dimensional tokens, some d of them, d rows and k dimensional tokens. Suppose if it's 1000 by 1000, then we need 1000 by 1000, which is 10 power 6, like a million parameters to actually store that. Now, if I do the same, here also I am doing the same W naught x I am taking, but here I am doing one small trick, which is I am taking another delta W and multiplying it with by x. And what is this delta W? This is kind of exactly the same kind of thing, but it is decomposed into two matrices, which gives me back this original matrix W, something like that. Okay. Remember we said the LLM, the intrinsic dimension of an LLM, the information stored in LLM is very low, it is over parameterized. So the number of rank, the amount of linear dependence that we can assume, the top n components that we want, r components that we want to get out, is going to be your rank parameter here. So instead of saying 1000 by 1000, I'll say something like 1000 by 2 and 2 by 1000. So again, it's multiplicable. So again, it becomes like d by k is again 1000 by 1000. But then now what we have done is, because this is only 1000 by 2 and this is another 1000 by 2. So 1000 by 2 is 2000. Another 1000 by 2 is another 2000. So it's just 4000 parameters. We already have a huge matrix here of billions of parameters. Now here we are saying, I think my intrinsic dimension is only in 2 or 3 or 4 dimensions I can capture it. Accordingly, I put a decomposition structure, and this structure itself is trainable. So the way I decompose, whether it's the moment I fix the rank, I can train these elements of these matrices, and now with 4000 elements and with this whole thing frozen, that's the key. I've taken all the stuff, the whole thing is frozen, but I've again taken a decomposition of this whole stuff through this way, which is very low number of parameters. That is a very good approximation of this one, and now I'm training only this. That's the beauty. So that is why I said here we are infusing something, this gray line. So we're infusing this part, making it trainable and learnable, and making it fairly manageable number of parameters. Still 4000 parameters is very low, but over multiple such attention blocks, if you think about it, over the whole thing, it's going to be huge. It's going to be huge compared to 4000, but compared to this millions and billions of parameters, it's going to be nothing. So now we have a manageable space. In every space, we took the contextualized embeddings, which is our multi-headed self-attention. We converted them into decomposable, trainable stuff, and we set the parameters nicely, and we learnt them over time, right? Over all the contextual chains. I mean, how beautiful we have done that, right? So we have kind of insurmountable problem because of this low rank decomposition. We have done a very parameter efficient fine tuning process. Okay, this is very important because of course you would have understood this, but the implications of this, if you think about it, it's very interesting. Now with this, what are the kind of implications that one can think about? Um, do we let me should we put this in every layer always, every contextual embedding layer, every multi-headed cell potential? Is it needed or not, or depends? It's always depends when I say depends, right? So it depends, right, actually, because I know fairly, I'm talking about English sentences. All the statistical patterns are mined enough by all the corpuses of the existing foundational models. So I'll do a simple low ranked approximation only in certain layers. I'm fine. But if I want to do some kind of a math reasoning, that's a completely different ball game, right? Or depending on the problem, now I'm free to choose what I want to choose. Now, when I visualize this layer here, what exactly it is doing, and then do the LoRa approximation, I can do some kind of a this canary runs, like saying like what really happens, get the insight, just play around with it, and then come back and fix a certain rank. Okay, the intrinsic dimensions are not enough if I take only certain context. Let me go a little deeper. Let me freeze more. Let me unfreeze more. I do all my games, right? So that's a beautiful way of doing this actually. So this is the key idea of LoRa, which not only reduces our thing, and it's not at all even. And if I put an alpha here and 1 minus alpha here, which means that how much of importance that I can give, and this is kind of captured in an alpha parameter, which I'll show you later in the code. Um, so this, how much of the foundational model knowledge do I want versus how much of the fine-tuned nuanced representation that I've added that I want to weigh more is something that I can also tweak. Okay, so very simple code walkthrough. It's not like very complex. Now think about this is the typical your from data sets you import all your import statements, and this is your PEFT. These are the main things that you would probably need for fine tuning. This is taken from a Hugging Face kind of a setup. You can use here Torch is used, and you can as well use Keras. I think Keras NLP layers are there, and Keras NLP transformer layers are there. So you can use the same thing in Keras. So you can take a certain foundation model, and this is where you got your model checkpoint. Some uncased distal bird. I think this is around 70 million parameters. You can go and see the model card in Hugging Face. Now, so you got an ID to label to ID, and you can take the model, and you have a corresponding tokenizer. And you guys all know what I'm talking about. You have done a lot of such things. So you can actually have a very low amount of data for sentiment analysis. By the way, this credits to Talebi here, Shaheen Talebi. He has got a truncated data set here, which I've taken from his GitHub. This is the code from his GitHub, and you got a label and you've got a text. Okay, and this is simple pre-processing for your tokenizer. Now what happens here is you can also put your accuracy. You can say that you can take the predictions from your foundation model, and then you can say and you can take the logits out, and you can say among all the logits, which is there are two logits, one is for positive and one for negative. If it's 0.5, 0.55, 0.45, then you know the argmax of those predictions are argmax of those logit predictions is 0.55, which means that is 1, which is positive possibly, and 0 means it's negative. So it's very simple kind of thing. It's accuracy calculation for evaluation parameter. If I take all that, and so I can give a list here. I get 1, 2, 3, 4, 5 kind of sentences. 5 sentences. It was good, not a fan, don't recommend, better than first one. All these 5 sentences. I take this list, and for each sentence in that list, I first tokenize that sentence and return the tokenizer, I can choose the tokenizer of my choice or whatever is given in that model card in that BERT uncased model and digital BERT tokenizer. And then I send my model, the real foundation model, send those tokenized inputs and then get the logits out from the reparameter. Here I'm not doing any fine tuning. This is just a plain foundation model. Get the logits out and take the argmax of logits and you take the predictions. So for everything you get the predictions and you just populate this list. This is it. And so it was good. It says it's negative. Not a fan, don't recommend, negative, possibly right. Better than the first one, not sure whether it's negative or positive, here it says negative. This is not worth watching even once, certainly negative. This one is a pass, negative. So here it kind of gets at least 2 correct, if I could say. It's kind of little bit worse than a random model. Let's do LoRa now. This part a little bit I'll go slowly because this is something that what we actually did, whatever we spoke, the code will flow like that. So think about the code. There is a task type which is a sequence classification problem. Here we are with the sentiment classification. Sentiment is nothing but a sentiment classification is nothing but classification of a sequence of words. So it is a sequence classification problem. We defined our task first, and we first tell the config what is the intrinsic dimension which we want. That r is equal to 4 versus 2 versus 1. So we thought 4 is good here. And this alpha, this is that weighting parameter, learnable parameter that I was talking about. And the last, there's a dropout. You randomly kind of flicker. And then you've got a target. What is a target module? So the query layer, the query linear layer of your transformer multi-headed self-attention. You can also do it for query key, 2 different things. So this is my config. So with this config, I actually send into my get pef model and I get the model. So I've set my model now. I come back to this right part now. I put a bunch of training parameters here and I give some training arguments. This is just a name, LoRa text classification. That's how my model will be checkpointed and stored in the Hugging Face. And I've given certain learning rate, I think it's 0, and batch size and epoch, all that. And then this is my training args. And in the trainer, I actually take the model and I give the training data set here. Here is where I give the training data set. I give the tokenizer, the data collator, and to compute all the metrics that we saw there, the logit evaluation. And then finally I train. This is how a LoRa is trained. The code part is very simple if you know all the concepts and if everything flows in clearly. Now after training, if you took the fine-tuned model and if you do the same thing, run through the list and then you do the thing, it was good, positive, not a fan, don't recommend, negative, better than the first one, positive, this is not worth watching even once, negative. I mean this one is a little tricky, so this one is a pass. It says it's positive, so it couldn't get the idiomatic expressions possible. So yeah, so maybe a little more R, if you increase the R, if you do a little more different ways of fine-tuning, you may get that. But this is certainly an improvement on that, right? This is fine-tuned with very low parameters using all the information that we did. So this is the basic stuff, the second point that I wanted to get out of this. Now a few sundries, the few sundries that I want to also pass through. It's 11:40, 10-15 minutes. Now there are a few other things other than LoRa. Now I'll go back to the chart, but before I go back to the chart, LoRa is one reparameterization way, and in that additive block where you infuse your own weights, there are different principles. Think about, now is a good point to revisit our prompting also. When you do prompting, if you really think about it, what you're doing is, you're kind of wading through the vector space. Now when you do prompting, there is no back propagation that's ever happening. It's just the forward propagation, a few weights are changed here and there, and the representation is learnt a little clearer. Okay, so it's basically saying the bank of a river is long. If you give some statement and you say you're in the context of a reading comprehension that is about a river, the more you give, like the bank of a river is long, the bank of a river is winding, you are kind of moving through the vector space and setting it to a context, a bunch of vectors here that are closer to dealing with bank as rivers versus a bunch of vectors in that dealing with bank as currencies. That's what you're doing while you're doing prompting. You're kind of maneuvering around the vector space. Now, the other thing that you can also do is you can do something called prefix tuning. Instead of making it as a hard prompt while you can give a prompt, and you can also say that the weights of the prompts in and around it also can be trainable. How do you make a prompt trainable? So this is a regular transformer block, and let's say you give a prompt here, which is a soft prompt. And why is a soft prompt? It comes along with some fully connected layer. The moment I say fully connected layer, there is a W involved, Wx plus B, right? So once there is W involved, the W will be trainable. It can get the backpropagation gradients. Now, the soft prompt along with this can be concatenated with the previous transformer blocks attention. Now, what is this? What is the other good aspect of a fully connected layer? I can always scale it down to a lower size dimension, which is equivalent to the embedding dimension of my previous transformer layer. So I got a 512 dimensional thing that is coming in. I got a prompt which is of any length, any dimension, but I know fully connected layers. I made it trainable A. I also made it the embedding compatible with whatever is coming, and then I concatenate and I do the whole process. Now in this way, if I do multiple soft prompts, then I've trained it very nicely over time, and I can use those weights. So it's already soft prompt trained. I'll put these weights inside concatenate, and I can do the inference time thing. Now this is a beautiful trick again. The second trick along with this is you can put, instead of having just one Wx plus b, we can also have. Am I still audible there? Okay. We still have an adapter here and an adapter here. An adapter could be in between uh, some fully connected layers in my transformer block. After self-attention, there is a nonlinearity infusion, and then my adapter block comes, and I can put predefined adapter blocks here. And these adapter blocks are nothing but some fully connected layers, again for learning and for passing the information, doing the dimensionality adjustment. So I capture a little more nonlinear expressivity here. So this part I can adapt. So I can infuse. So all these things I am infusing in the original architecture. And that is why, I don't know if that diagram will immediately come, but I don't mind going back to that diagram, saying that your soft prompt tuning here, which is based on your soft prompts, are really a part of your additive models, and as is your adapters. They are also a part of your additive models. And LoRa almost is. The only thing is you a little bit reparameterize it. That's the only difference. And the selective is you randomly select. You don't necessarily follow any pattern. Now we are coming to the end of the talk. There's something also called llama adapters. You can also, along with whatever the adapters you had, you can put some gating factors. This could be a 0-1 kind of a gate, whether it's open or closed. Depending on that, this context, I want to little bit more expressive with this context, but in the next context, I don't want to be more expressive. It gives a little more power to you. So that's, and that power can be in terms of your key or a value. You can change it. So this is kind of, I mean, I'm sure with this kind of a background, if you go on, you can go and read the additional nuances, and you can find out the other things. And here are some methods that we saw in that slide, and here are the storage, here is the memory, and here is whether a backpropagation is involved or not. Most of the times backpropagation is never involved, because the moment you do a backprop, that's a lot of time spent. A, there's a lot of time spent. B, there is a lot of memory involved, depending on your floating point precision that you use for your weights. So none of your fine-tuning schemes would really do this backprop here. Some of them may be little memory intensive, may not be memory efficient, but most of them would be storage efficient, right? You don't want to store all the things, you want to store only a few things. Now let's take, thanks a lot. I think because we are in this slide, we'll take a 1 minute detour and understand how do we save space here actually. That will be interesting. So if you think about all this billion dimensional things in the forward pass, right? Depending on your batch size, if your batch size is 20, 32 or 64, whatever it is, only once in 32 times or 64 times, your back propagation will happen. But when you do a back propagation, two things I said. A, so your batch size times your back propagation, the number of weights. For each weight that you are adding, for each byte of memory that you are adding, their optimizer, something like an Atom, will actually need some storage. The optimizer needs your to store the first moment because you have to minimize a loss function in your back propagation step. For that, the first moment has to be stored. Your second moment also has to be stored, right? And all the gradients have to be stored, right? And the higher your parameters, the higher your batch size, and the higher your byte size that is needed in that memory, these number of parameters are going to be more. The amount of space the Atom optimizer is going to use more. And also that is why the number of parameters we are trying to reduce in a LoRa kind of scheme. So that is what reduces the memory footprint and also increases our ease of operation. Anyway, that was a detour, but it's a little bit into the internals of it. Yes, the last one, we'll go a little bit faster in this. There's something called RAG, retrieval augmented generation. So what if this is the doctor example that I gave. I'm a specialist neurologist and my LLM was trained in all kinds of medical documents, but it does not know my cerebral ataxia, all the recent classifications, and whether it's due to some histological concerns or autoimmune disorders or genetic disorders, etc. So for that, I can actually give a context here. It can pick the context along with the prompt. It can pick the context and then it can send it to LLM. And how does it pick the context? My context, I am converting that into my embedding. My whole data that I have, I am converting it into vectors, and these vectors are stored in a vector store. So my search is going to be even when something is approximate, I will get the answer. It's not a keyword search like a SQL. So it's an approximate search, and there are a lot of advantages using vector search, right? So it's very fast to start with, and it's also approximately accurate. So I've got a vector database. Yes, but document source. I split the documents into chunks, and I make sure these chunks kind of overlap, like first and second, second and third, third and fourth, fourth and fifth. Because if I get stuck in those interfaces, if a query comes in the interfaces, I'm not stuck. I take both the chunked embeddings, and put the context, create the context that I'll put here. Take the prompt, take the context which I've taken out of this vector database, and send this along to my generative AI, the real foundation model. So all this paraphernalia is available for me. I train this offline, create my vector database, and using this vector database, I contextualize and send the whole prompt and context to my LLMs. You got that flow, right? That's simple. So same architecture in a different way. Same architecture again in a different way, but again, so you've got your foundation models, the LLM, you've got your memory. Like this need not be just my information, this could also be your memory. This could be some feature stores, my own features that I mine, and this could be some tools or agents that I want to push in. I want a reservation agent uh, to be actually, this is all about some ease my trip or make my trip kind of data and my travel plans, possible travel plans. All that is my personal data, and I put my personal agent and I give that agent some priorities. That also can go. And chain everything in the final chain. I can make a QA system out of it. I can make a chatbot. So this is very useful for my enterprise kind of setup. And this is something that I did for a small medical example. And this is the Chroma DB that I used as my vector store. And in this vector store, all my vector embeddings are stored. And I can use any kind of embedding to create those any kind of embeddings like OpenAI's embedding, um, files, whatever it is, and I store this as a vector store. and I use my data here, my data which is Gale.pdf, Gale encyclopedia that I have it, which I assume that it is not having, and this has been converted into vector database here. And now based on this, whatever the QA system I trained, I asked a question, I created a chatbot out of it. I asked a question, what is uh, what is myasthenia gravis? And here I purposely gave a spelling mistake in a technical word, and since it's vector search, it took my specific thing, whatever I had, and it actually gave me the answer. And some general purpose questions I gave, it was not, it was there in my corpus, but it was better in some other foundational models knowledge trained weights. It was able to mix the best of both worlds and give to me. So that's some kind of a simple application also for you. And there are a few more things, but I think it's a good point to stop and talk a little bit, because the few more things that I also had was, what if we have multimodality? What if we want to fine tune videos, audios? It's a little involved, but I think we'll get into it in a separate offline call. There's multi-way, multimodal transformers. What if your attention matrix is not a 2 by 2? It could be a tensor, could be an attention tensor, right? So all these things are possible in real world, and this field is awesome and very rewarding, very challenging as well. Awesome. I hope at the end of this you had solid attention weights during the talk and you are a little bit fine tuned. Like, yeah, awesome, awesome. Thanks for your patient hearing. And I can take questions from online as well if someone wants.
So questions, please put up your hand.
Or it need not be with fine tuning per se. It could be anything. You can even convert this into AMA session. Ask me anything.
So
If I know it, I'll say. Otherwise, I'll say I don't know.
so what's next? Like in OpenAI, they're talking about some upcoming AGI heralding Q star algorithm.
Beautiful, beautiful.
So if you could share some.
Awesome. So the question was about AGI. By the way, I have to give a little bit of background about AGI because not everyone will know AGI. Have you guys heard about automatic artificial general intelligence, which AGI stands for? Like, very quick idea. How many of you know I've worked on an AGI? I don't expect much. Okay, great. How many of you have heard this term and kind of read a Medium blog or something around it? Okay. Okay, like 10% or 15, 20, 25% of the audience. Great. So let me go back to one thing here, which is this part here, right? The toolkits and agent executors that you see here. This is something that people can evolve. So the frameworks like LangChain, they generally kind of pace it up themselves in a certain way that if they want to actually use some kind of an agent, which an agent can be someone which trains multiple models, which takes multiple fine-tuned models and gets an output, and then it says that no, with this kind of question, this guy gives me a better answer than this. So that kind of a finite state automata infusion is possible with this kind of an agents here. And the more the finite state automata and the output that I have, the ability for me to convert that output into some kind of an intermediate representation as I do it along multiple times. Now I know this, so I become like a compiler. I know if the request comes like this, I'll do this. I create that intermediate representation, and in that intermediate representation space, I become very smart. So that is the level of general intelligence that this particular field is going towards in an applied fashion. In the fundamental research of AGI, a lot of things are being done. That is separate. But in an applied fashion, this particular part is becoming. LangChain People have been using LangChain a little bit for AGI. You've got heard about Baby AGI? There's a GPT, there's a GitHub on Baby AGI. I would request you to go and just check that out. Yeah, yeah. In the theoretical side, there are a lot of things I couldn't answer that all that completely, but applied side. The other question, you had a question. Oh, sorry. No, there was a question there. I'll come back to you. So, sorry, you said Laura? Mhm. No, no, no. We do back propagation. We do back propagation in LoRa. In prompting, we don't do back propagation. In LoRa, we do back propagation. They will learn. They will learn. The only thing, the number of learnable parameters is just like you said. You saw 1000 by 2, that is 2000. Another 2000, 4000. Because the other things are all frozen. The millions of dimensional parameters are all frozen. So 4000 per layer. Let's say like 22 layers, which is reasonable for me. Yeah. Sorry, I'll take him and come.
Sir, how we can evaluate the embodied models?
How can we evaluate the?
Embodied models.
The question is, how do we evaluate the word embedding models? There is no actually one answer to this because it depends on what we are evaluating against. If you are evaluating for a task, it is a little bit task dependent. If you're evaluating for a sentiment analysis like that, and you saw the way we evaluated. But if you are evaluating on a broad stroke thing, which is needed, which is scalable for every other task, right? Something like a multitask kind of setup, then you have to have your own alpaca kind of data set yourself. So alpaca has created its own data set and it has its own metrics reported for different foundational models. And if you have a new model, you can train it over their data set and report the benchmarking thing. The only way is to benchmark because you can evaluate over existing benchmark data set. Or if you think that you have a very specific case, you can create your own benchmark. Like suppose I'm creating a bunch of mammogram labeled data. There's a bunch of mammograms and I've explained the mammogram in a certain way given the image in a multimodal setup, and that expression is very unique to me. So when I do my fine tuning, whether it works or not depends on my own metric and my own way in which I express that particular thing. So if it's that specific, then you'll have to develop your own benchmarks. We'll go back to your question.
One thing that you said Laura is adding a lot of weights. So if I have I understood it correct that the fine-tuning fine-tuned model is better. It will have a little bit more number of weights than the business model.
Okay, so the question is, will the fine-tuned model have more number of weights? Correct, it will. A fine-tuned model will have more number of weights, but the number of trainable weights will be far lesser in the fine-tuned model. Correct.
The other question was regarding the personal blog which you showed.
Okay.
So intuitively, how would it be different when we add more transfer of blocks probably and we increase the heads instead, attention heads instead, from the perspective.
You're talking about this, right? Okay, so the question is, how will this be different if we have more and more guys here at the multi-head attention, like number of heads is more, and more blocks here. This is one block, like that we've got 88 blocks, for example. So this one has a very specific reason. This actually builds a context. So this builds a context around the bank of a river is long. The bank of a river, it has disambiguated. That is one thing. One head has captured that. The second head, it is long, windy or not. Is it across a habitat that is having a lot of high races? All that. Different heads capture that way. So this is at this level. Now when I go to the next level, no, this has got a lot of high rises. So this probably is talking about a city. And the city that it is talking about is Paris, because this is somewhere I saw River Seine or something like that. That is something that will be a context for the deeper down transformer blocks. And because the way I chain these transformer blocks again and again, I captured this long range dependencies, which is the original purpose why I put my transformer block. Because transformer is a model which has a the inductive bias is very special, right? It has no very low inductive bias. In a CNN kind of a model, I have parameter weight sharing. So my 3 by 3 kernel passes and then it passes to my right. So the weights are kind of shared between one pass and the other. There's a good amount of weight sharing. So there's a lot of strong inductive bias that way. Here it's the inductive bias is very low, so it is able to capture long range dependencies. But the problem that comes with capturing long range dependencies is you need so many blocks of it because the range has to be that long depending on your context length. That's one problem. Second problem is because you need so much of ambiguation, different features in which you have to capture. The third problem is intrinsically you are looking at how one thing is related to your own thing, the number of tokens. So all these things put together will create so many number of parameters that you need. It is a data hungry model, the bunch of transformers. So it's become very data hungry. So this whole transformer kind of models, if you train with very less data, you're over parameterizing them, which means there's a very high chance that you are kind of rote learning or overfitting. That's a question here. How are GPTs? Uh-huh. Oh, custom GPT you're talking. Sorry, I didn't get it. Sorry, you also built one. Yeah, yeah, awesome. Yeah, I mean, so fine tuning is a way of doing one of the three things that I showed you actually. So either tailor it for a specific request. When you say custom, that's what you're doing. Second, you're either constraining or you're adding some data which was not there. Your custom thing has added something more. Or fourth or third is like you're adding new knowledge to your foundation model which was not there. So it can differ in any of the three ways depending on what you really set out to do. There's a question there.
Let's say instead of recreating like model on asking different ways of parameters, if you create it like only with one and just maybe the people perform like it.
So the question is for, for the benefit of audience online. The question is, so we did all this and we reduced the number of trainable low ranked approximation parameters. What if we in the first place used this many less number of parameters to train rather than do all those things? Two problems. One is when we initially trained, we trained with a huge corpus. A huge corpus, it had the probability of that capturing all kinds of statistical patterns across different domains is very high because I've given millions of documents, and to actually resize my parameter potential to that millions of dimensions, I needed that big and expressive model. Maybe that decomposed small versions of it may not do justice to it. That is the reason why I trained with lot of all those things and I froze. But right now I want the best of both worlds. I want all that knowledge, but I also want some retrainability because I've got a little unique kind of data. So now I freeze everything and I do a little bit of decomposition, infuse these small things into that particular transformer in every layer. In that particular transformer block, I infuse this and I change that weights. I do a small delta W dabbling of that weights, and then now it's kind of fits my purpose. That's the connect. I saw a question somewhere. Okay. There is no restriction on the data set in which you can fine tune. It can be a plain text. like what the format they use in the foundation model, or it can be a graph or whatever you have, but ultimately converted into a vector and whose vector embedding matches when you concatenate it at the right layer. That embedding should match. Your original thing can be anything, but you ultimately have to convert that and put it into this thing so that that mechanism can flow through. Yeah, sure, of course.
Context link is still a challenge. Context link is still a challenge with the RAG, right? Although OpenAI and other models like they are coming up with a larger lens. So does it make sense to take a foundation model to train it on a specific domain, specific data, or should we just go with the RAG?
Okay, that's a very it's little involved question. The question is, um, the context length is still a challenge. RAG is kind of efficient, but not still there. Can we just use the foundation model just to train our own stuff? Two problems. Straight away, some foundation models you don't get the weights, so you can't do it. Assuming that you've got a foundation model where you have the weight, open sourced, the challenge would still be the over parameterization, because of which the bias, like how are we going to overfitting bias, that you'll have to take care of. The third problem that I see is, of course, it's expensive, setting it up and all that is a problem. There is something called forward looking FLAIR, right? Forward looking augmented retrieval generation. So right now we are getting into the next stage of RAG, where the RAG is actually combined with some knowledge graphs. So that probably can address a little bit of the accuracy problems. But your fundamental question was, you had a context length issue. The context length issue converts into my attention matrix size, right? I mean, so that becomes purely a computational problem. That is a very hard problem. So this will ease out only when you have the right either the hardware or the right LoRa kind of, or a qubit kind of mechanism, QLoRa kind of quantized LoRa kind of mechanism, where you can vastly reduce your memory footprint, because your context length, attention vector, memory footprint, you really want to reduce it, you have to quantize it along with LoRa. So there are things like QLoRa which can do it. There's somebody called Tim Dittmers. You can see the bloke, that is his Hugging Face card. This guy has a lot of good ones. That's one way in which you can think about it. There's a question here.
So how can we use OpenAI in the stock market, like for trading purpose and investing on suppose I'm planning to like start up of a charity firm. So how can we use OpenAI for that?
Right. Um, I'm not an expert in this, so I have to just say something that I know. So the question is, how do you use LLMs and fine tuning in high frequency trading, SFT? So high frequency trading for people who are not aware of it is like, I want to trade, but I want to get information at even a millisecond or microsecond scale sometimes, like whatever happened immediately in the last minute or second, what kind of newsreel went up, what kind of company statement came in, all those things um, uh, affect your day trading, or I mean that much frequency in which your trading gets affected at a minute scale. So your arbitrage becomes highly efficient if you're able to capture all those signals and modes. Is it a fair explanation of high frequency trading? So yeah, the faster you can get it, the better you are in your decisions. Now the question is, how do I use this kind of fine tuning models for setting up your good pipelines for high frequency trading, right? I mean, right away, one good way is to actually start. Yeah, you don't need to start from scratch. there are some foundation models available like Finance GPT and stuff like that. That's for the familiarity with the domain, the response kind of things. Second, you need to fine tune here because depending on the kind of, if it's a Shanghai thing, whether it's the Kospi or the Kospi or the Nifty versus Nasdaq, or depending on the markets, there will be different elements that will be impacting that. So you need to have which element as is a part of your purview and make your own data sets over time. And over time, you actually condense these data sets and give some kind of a summarized entries. Now you make it like a key value, some kind of a dictionary entry with whatever you think are the is the key and the values of the dictionary for your market, your thing, and your the smart signals that you're, yeah, all kinds of signals, and you create your own data set. And with this data set, infuse in your foundational finance GPT or something like that, and give these additional parameters. Now I'm in a day session on a Monday after a weekend, where whatever, give for that particular ticker symbol, you give the context, you change the context, and you set up something like that, and then you can do the fine tuning using any of those methods. But the key here is how much of a reinforcement learning with feedback that you can put in. So you can, this is where you can use RLHF in a very good way. So how many times has this given me a reward of plus or minus? Uh, Sorry? Yeah, it's kind of related to accuracy. Yeah, but it's more related in my mechanistic setup to the decision making, whether I need to sell it or when you need to short something that I have in that or not, whether I'm going to go to for a swap or whatever it is, forward swaps, whatever. So all the decisions, here are my decision points and here are my decision variables, and this is how it has progressed. So you can make something like that also. So that'll be very interesting. Most certainly, they use techniques like this. I don't know if they exactly use this, fine tune it in the way I said, but they use something like this. They'll definitely use a very good smart signal pipeline. All that smart signal pipeline will flow into their data lake, will be stored in their data mart, and it will be accessed in real time. They'll probably running some Spark jobs or some Storm jobs, Apache Storm, or whatever be your open source tool or enterprise tool. They'll use that accordingly to mine out some important features, and they'll put some deep neural network models to say that this is the right time or this is not the right time, or even the quantity of it, how much you need to trade. Yes. And over a period of time, they probably take small steps so that they get the reward also. They have a huge data, and now they learn over that data and then again use that, using all the features and using the learned data, they can use it for high frequency trading. Yeah, cool question. Okay, you got two questions. I'll take two. Yeah, beautiful. Every talk I give, this question comes. I thought this question will not come with that. I'll answer the question. I'll take your question.
Context,
Yeah,
where accuracy is very premium, very
correct,
much required.
correct.
How do you combine, let's say, like you said, knowledge graph, rags, and then chain of thought reasoning?
Correct.
Is there any approach how you would like combine it, like the models?
True. So there are a lot of
Like
approaches.
100% accuracy, just like mathematical logic, which is the gold standard.
Right. In fact, a lot of ways in which this chain of thought itself. Right now, we can say it as XOT. COT is the chain of thought. You can nowadays you can have a tree of thought. You can have a graph of thought. You can have a thought of thoughts framework. There's a lot of different things have come up. So basically, what all this means is you got a verbose structure in which you are explicitly soliciting the internal representation and the logic in which an LLM is pursuing about its task. You are making that come out. So chain of thought is like, I've got 3 apples worth 2 rupees each, and I already had 10 apples. So how much is it? Like 3 into 2 is 6, and I already had 10, 10 twos are 20, 20 plus 6 is 26. So you need to combine all these pieces, and sometimes you need to go into different parts to get these different pieces and assemble them together, and then put the mathematical logic, where I can say, here is my mathematical agent, here is my fruit agent. Now this is the time to call my fruit agent mathematical agent, and there's an overseeing agent, and you combine everything. So that is the whole chain of thought, and that can be a tree of thought. Sometimes your chain of thought is like, it's not clear, I'm not getting anywhere, so I'll go back and form a different path. So that's like a tree of thought. So there's a different trees that you can form. There's a graph of thought. Knowledge graphs are kind of related to that. So there are different ways in which you can
Be at the level of that
agent execution.
supervision.
Correct. That will be at that level. Now coming back to the last, is it the last question for the day or? Okay. So the last question is, how do you treat the trust bias of an LLM? It's not a question. It's a kind of a big. It's a paradigm in itself. So trust, fairness, bias is all there. There are different ways in which you can do. LLMs can be, what do I say? Can be kind of tricked. One is jailbreaking. Have you heard about jailbreaking? Yeah. So for people who have not heard about jailbreaking, it's like, you systematically handhold an LLM using some prompts to exactly make it do something for which it is not intended to, or to exactly get some information from it which it has stored in its knowledge base that it is not supposed to reveal. So you can prompt in a certain way, and you can get it out. And I think there are a bunch of professors who had a paper on LLM, the way in which you can, the privacy of LLMs. I think it's from University of Lowell, I guess. So they had this observation that a lot of these LLMs can be broken. One of the LLMs that is little hard to break is Chat GPT-4, but still it's breakable. It's not that it's not breakable. It's a little hard to break. They had some hundreds of tests, thousands of test cases in which all the LLMs, whether it's enterprise LLMs and or open source LLMs, all of them are susceptible to some kind of a breaking point. And the only thing, as a rough statistic that I remember, ChatGPT 4 was very hard to break. Still it's breakable. Some of the easier ones were some of these open source LLMs were very easy. The next hard ones to break were something like Llama or things like that. Things like Vicuna or Mistral, they were very easy to break, based on that paper. So yeah, they are very easy to break in terms of that thing. So that's about the security part that you asked. The second part is the trust. The trust bias issue of the LLM is again the same old problem that we had with all our machine learning models. If I had a lot of data trained where the nurse, as and when I say a nurse, I always attach it with a female. So there is a gender bias that is implicitly fed when I do the training. So the nurse has to be a female, is some kind of a knowledge weight it has been stored. Oh, since it has gone as a nurse, one kind of a neuron always fires, and that kind of gets stored as a weight which is always high. And if that weight is high, some feature is always triggered, and that feature is related to an auto completion task which says that nurse means it puts the next word as she and not a he. And all this because of my training corpus. That's gender bias for you. Trust. Trust is again a problem because of training also, because the way I give my data, historically I had given a lot of data where, for example, it's a financial data where I had given a loans. There are few parameters I have heavily weighted on. I weighted on socio-economic conditions a little bit, repayment capacity, which is okay, but that is related to socio-economic conditions, which could form its own connect to some racial group, or which should form its own connection to a locality. So that's like really bad, right? You don't want that. So every case is different. So you don't want to generalize any location or any population group or anything that way. So that's a problem which comes with training corpus. But in order to do that, how to attack this? And this is where it comes, which is similar to how to attack this. You can't completely solve it, because the one way to think about it is use explainable AI to actually see why which attention layer was triggered, what context was triggered high for that kind of an auto completion or down the task decision. If you know that, then you can kind of underweigh or overweigh that. You can say, you can put another meta model to say that I have high confidence in this versus low confidence in this. This is trustable, this is gender bias low, this is population group biased high, something like that. You can give some kind of a vector. So put you can actually create a high dimensional vector space based on all the parameters that you have, and then you can create based on your decision how aligned is your decision vector for all these red vectors in your that space. You can do something like that, some meta model at the end. Right now, that is the practical thing for enterprises. That's what I think.